The objective of this lecture is to provide solutions to the first theory assignment. Question 1 is as follows. Let U be a vector with constant magnitude. Prove that the rate of change of the vector in frame A dotted with the vector itself is equal to 0. So here's the solution. We know that U has constant magnitude, so that means that the magnitude of U is equal to a constant. But the magnitude of U is equal to the square root of U dotted with U. So that implies that U dotted with U is equal to a constant because U dotted with U is the square of a constant, which is yet another constant. So that implies that d dt of the magnitude of U squared is equal to d dt of U dotted with U is equal to 0. And the rate of change of U dotted with U can be taken in any frame because U dotted with U is a scalar. So that implies that I can take the rate of change in any reference frame, so I'm going to arbitrarily take the rate of change in frame A. That gives me d dt in A of U dotted with U, which is equal to du dt in A dotted with U plus U dotted with du dt in A, and that's equal to 0. But du dt in A dotted with U is equal to U dotted with du dt in A, so that gives me 2 du dt in A dotted with U equals 0, which implies that du dt in A dotted with U is equal to 0, which is the result that we wanted to prove. So that's the solution to question 1. Question 2 is as follows. Let dB dt left superscript A be the rate of change of the vector B as viewed by an observer in reference frame A. Explain why dB dt left superscript A is observed the same in all reference frames. So the solution to this problem is as follows. dB dt left superscript A is a vector. A vector is any quantity with magnitude and direction and is independent of the reference frame. Therefore, dB dt in A is independent of the reference frame. And is thus observed the same in all frames. as observed the same in all reference frames. Let's do question 3. Question 3 says, let omega B A be the angular velocity of reference frame B as viewed by an observer in reference frame A. Prove that omega BA equals minus omega AB. So for this problem, the solution is as follows. We know that omega CA is equal to omega BA plus omega CB for all reference frames A, B, and C. So therefore, if C is set equal to A, we have that omega AA is equal to omega BA plus omega CB. But omega AA is equal to 0, which implies that omega, sorry, this should be omega BA, AB. So, therefore, omega BA plus omega AB is equal to 0, which implies that omega BA is equal to minus omega AB. Question 4 is as follows. Let omega BA be the angular velocity of reference frame B as viewed by an observer in reference frame A. Prove that d dt in A of omega BA equals d dt in B of omega BA. So the solution to this problem is from the transport theorem. We have that d dt in A of omega BA is equal to d dt in B of omega BA plus omega BA crossed with omega BA. But omega BA crossed with omega BA is equal to 0, which implies that d dt in A of omega BA is equal to d dt in B of omega BA. Question 5. Let E1, E2, E3 be a right-handed orthonormal basis for three-dimensional Euclidean space. Prove that dEI dt in A for I equals 1, 2, 3 cannot have a component in the direction of EI for I equals 1, 2, 3. Okay, so let's look at the solution to this problem. So there are two ways to do this. The first way is perhaps a little bit more. And actually, we have to put one more thing here. We can write this. Assume that E1, E2, E3 is fixed in B. So it's fixed in a reference frame B. That's actually part of the problem statement. So we can do this one of two ways. We know that the rate of change of a basis vector in frame A is equal to its rate of change in frame B plus omega BA crossed with the basis vector. But that's just equal to omega BA crossed with the basis vector because this rate of change in B of the basis vector is 0 because the basis vector is fixed in B. So as a result, dEI dt in A is orthogonal to both omega BA and EI, which implies that dEI dt in A is orthogonal to EI because the cross product between two vectors is orthogonal to both of the vectors, which implies that dEI dt in A cannot have a component in the direction of EI. That's the first solution. The second approach is as follows. Is that EI is a unit vector, which implies EI has constant magnitude. So that implies magnitude of EI is equal to a constant, which in this case is just equal to 1, which implies EI dotted with EI is equal to a constant because EI, the magnitude of EI is the square root of EI dotted with EI, and that's a constant, so EI dotted with EI is a constant. And that implies that dt of EI dotted with EI is equal to 0. But that's equal to, since I can arbitrarily differentiate this in any frame, that's equal to dEI dt in A dotted with EI plus EI dotted with dEI dt in A. And that's equal to 0, which tells me that 2 dEI dt in A dotted with EI is equal to 0, which tells me that dEI dt in A dotted with EI is equal to 0, which tells me that d, e, I, dt, and a cannot have a component in the direction of EI, because DEI, DT, and A and EI are orthogonal to one another. So now let's go to question 6. Let U1 and U2 be orthogonal unit vectors. Prove that du1 dt and a dotted with u2 is equal to minus u1 dotted with du2 dt and a. So here's the solution. Because u1 and u1 and u2 are orthogonal, that implies that u1 dotted with u2 is equal to 0. So that implies that the rate of change of u1 dotted with u2 is equal to 0, which implies I can take the rate of change in any frame I feel like, because u1 dotted with u2 is equal to a scalar. So that's the same thing as taking the rate of change in A of u1 dotted with u2, which implies that du1 dt in A dotted with u2 plus u1 dotted with du2 dt in A is equal to 0, which implies that du1 dt in A dotted with u2 is equal to minus u1 dotted with du2 dt in A. Let's go on to question 7. So question 7 says, let A and B be vectors that lie in E3. And let A dotted with B be the scalar product between A and B. And also let E1, E2, E3 be a right-handed orthonormal basis for E3. Show that A dotted with B expressed in the basis E1, E2, E3 can be written as A dotted with B expressed in E is equal to A1, B1 plus A2, B2 plus A3, B3, where E is equal to E1, E2, E3. So here's the solution. We know that A and B can be expressed in the basis E1, E2, E3 as follows. And then B is equal to B1, E1 plus B2, E2 plus B3, E3. So therefore, A dotted with B is equal to A1, E1 plus A2, E2 plus A3, E3 dotted with B1, E1 plus B2, E2 plus B3, E3. And because all the cross dot products that don't involve EI dotted with EI are all 0 because this is a right-handed orthonormal basis, we get A1, B1 plus A2, B2 plus A3, B3. Now, we also know the vector A expressed in the basis E is equal to A1, A2, A3, and the vector B expressed in this basis is equal to B1, B2, B3. And we know that A expressed in the basis E transpose times B expressed in the basis E is equal to A dotted with B expressed in the basis E, but that's equal to A1, A2, A3 times B1, B2, B3, which is equal to A1, B1 plus A2, B2 plus A3, B3. So that implies that the scalar product expressed in the basis E is equal to A1, B1 plus A2, B2 plus A3, B3. Question 8. Question 8 has the same setup as question 7 does. A and B are vectors that lie in three-dimensional Euclidean space. B vectors that lie in three-dimensional Euclidean space. And let A cross with B be the vector product between A and B. And what we want to show here is we want to show that A cross B expressed in the basis E1, E2, E3, which is going to be defined as E, can be written as A cross B expressed in E is equal to the following matrix times the following column matrix. So let's go through this. So where we said that A expressed in E is equal to A1, A2, A3, and B expressed in E is equal to B1, B2, B3. So here's the solution. So for this, we know that A is equal to A1, E1 plus A2, E2 plus A3, E3. B is equal to B1, E1 plus B2, E2 plus B3, E3. So therefore, A crossed with B is equal to A1, E1 plus A2, E2 plus A3, E3 crossed with B1, E1 plus B2, E2 plus B3, E3, which is equal to. So now let's take the cross products. All cross products of any vector with itself is 0. So I get A1, B2, E1 crossed with E2 is E3. A1, B3, E1 crossed with A3 is minus E2. So I get minus A1, B3, E2. The next one is E2 crossed with E1, which gives me minus A2, B1, E3. And then E2 crossed with E3 gives me plus A2, B3, E1. And then E3 crossed with E1 gives me plus A3, B1, E2. And then E3 crossed with E2 gives me minus A3, B2, E1, which is equal to, well, let's gather up all the E1 terms. I get A2, B3, minus A3, B2 times E1, plus, I've got the E2 components. The E2 components give me A3, B1, minus A1, B3 times E2, and then the E3 components give me A1, B2, minus A2, B1 times E3. So therefore, if I express the cross product in this basis E, I get the following. I get A2, B3 minus A3, B2. And then I get A3, B1 minus A1, B3. And then I get A1, B2 minus A2, B1, which can be written as the following matrix times B1, B2, B3. So the first row, I'm multiplying B3 by A2, I'm multiplying B2 by minus A3, and I'm multiplying B1 by nothing. In the second row, I'm multiplying B1 by A3, B2 by nothing, and then minus A1 by B3. And then in the third row, I'm multiplying A1 by B2 and minus A2 by B1 and 0. So that actually gives the result that we were looking for. So the last question is as follows. Question 9 says that let A and B be vectors, in three-dimensional Euclidean space. Show that the vector triple product, or the triple vector product, A cross B cross A, can be written as A cross B cross A is equal to A dotted with A times B minus A dotted with B times A. So the solution to this problem is as follows. We know that the triple vector product can be written as A cross B cross C for three vectors A, B, and C is equal to A dotted with C times B minus A dotted with B times C. So if we let C equal A, then we obtain A cross B cross A is equal to A dotted with A times B minus A dotted with B times A, which shows the result. So that gives the solutions to all of the 9 questions on the first theory assignment, and can look through these and see if there are any further questions about these theory questions.